me get my PowerPoint. Okay, here, let's try this. Okay, great. All right, so good morning, everybody. Welcome to the weekly ESIC webinars, and today's webinar is sponsored by the Advanced Grid Institute, AGI, as well as ESIC. So to start us off, while we have people joining us, we want to just share a little bit of an introduction. The Advanced Grid Institute is a partnership between WSU and PNNL, and we have webinars monthly. And so this is our last one for this semester. We take a break over the summer, and this is just a little bit if you want to learn more about AGI. Then we have our ESIC, our Energy Systems Innovation Center, and ESIC is at WSU, and we have a group that also does weekly webinars, and I believe this may be the last one we have from ESIC as well. But that's a place you can go to see the different webinars, and eventually the videos will be up for this video. The videos and PowerPoints are up for these videos. So you can go to this website to learn more. So today we have our presentation by Kevin Schneider and Gautam Kandaperumal. Sorry about that. And Kevin, are you going to go first?
Yes, I am. Can I go and just share my screen?
Yeah, I'm gonna stop sharing and let you share your screen, and then I'm going to do a quick bio for the two of you while you're getting yours set up.
My screen should be shared now. Can you see it?
Yes, it is.
Excellent.
So let me. All right. So a little bit about Dr. Kevin Schneider received his BS in physics and MS and PhD from electrical engineering at the University of Washington, but we adopt him as a Coug. His main areas of research are distribution system analysis and power system operations. He's the chief engineer at PNNL and the manager of the distribution and demand response sub-sector. He is also a joint appointment with WSU and a research professor as part of the Advanced Grid Institute, and he is a fellow of IEEE, as well as the past chair of the PES Distribution System Analysis Subcommittee and the current chair of the AMPS committee. So is very active in IEEE. Gautam is currently a PhD student in EECS at WSU and is part of our Distinguished Graduate Research Fellowship Program, spending time at PNNL. And his work is the quantification of distribution system resilience, resilient design, and received his bachelor's degree from Anna University in India and his master's from Arizona State before joining us here. And he also worked for a while at Affiliated Engineers in Madison, Wisconsin. So I'm going to turn it over to Kevin and Gautam to talk about their research. So thank you so much for being here.
Thank you very much, Noel. I'm afraid my presentation doesn't seem to be advancing properly, so I'm going to share the screen like this. Does that look okay? I know it's not ideal.
Yes, it should be. So try now and see if it works.
Okay, I'll try one more time.
It may have been because my screen.
I'll just go ahead and minimize it. Like that. As long as that's okay, I'll go ahead and start so we don't waste time on that.
Sure, I think that'll work fine. It's still pretty big.
Okay, excellent. So this presentation is looking at some work that Gautam and I have been working on for the past year and a half now. And I will be going over some similar material to a presentation I gave here a couple months ago, but I'll be giving a slightly different focus. And while the topic here we're looking at is how we can look at the application of network microgrids for resiliency and decarbonization, how they can be a resource to that end, what we're really looking at is what are the controls that enable that, and what is it that you have to take into account when you're simulating and modeling it. So I will be going over the first part of the presentation, which will be looking specifically at the resiliency and decarbonization efforts, where we've deployed some various controls around the country. And I'm going to be talking about the algorithms, the implementation, the architecture, and then Gautam's going to look at how he's used co-simulation to start to evaluate what is the impact of latency and other considerations within the communication system within the control systems. And so that's becoming more and more of a consideration. We'll see that as we go forward here. So when we look at the overall use of microgrids, there's a lot of different functions that people can get from them. But two of the biggest that we've seen are resilience, and emerging more so now is decarbonization. And this is going to take a more and more important role as we go forward in the next decades. In particular, what we're starting to see is a transition from the legacy, completely centralized electrical power infrastructure to one where we're seeing more of a distributed, not just a control structure, but also location of assets is becoming more distributed. And additionally, we're seeing more of a push towards a decarbonization of the generation sources. There's a lot of really aggressive numbers out there, but some of the common ones are that in the 2030 to 2050 timeframe, we're looking at something in the order of 30 to 50% of electricity production coming from low to no emission generation sources. And we're going to see an increasingly large number of these sources being located at the distribution level. So this is really a combination of both the decarbonization and the fact that you've started to distribute the generation sources. We're also going to start to see a lot more power electronic devices, because many of these new sources, such as solar, are connected through a power electronics device. Also true of some wind turbines, but not all of them. And then we're also going to see more participation of the end use customers. And so what we're seeing here is a trend towards the reason that we had the centralized systems was because economies of scale, efficiencies, and ease of control. That's why we had the large central generating units in a centralized system. And because the fuel sources that were available, they were carbon intensive, to a system where, because of the deployment of more resources on the generation side, closer to the end use loads, additionally, the increased number of controllable assets, as well as the improvement of control systems, means that microgrids start to become an obvious consideration, because now you have some generation near the load. They're more of a decarbonized source. And so there's a lot of questions about how can they become a resource for the larger system. And these are some of the things that we start to examine. The big part of this, when I think about microgrids, is really the operational flexibility that they provide. And what I mean by that is, in a traditional system where everything had to be centralized, the addition of assets at the edge actually caused a lot of integration challenges. Whereas nowadays, the controls and capabilities that you can put at the edge, they're at the point now where they can be semi-autonomous, or in some cases even autonomous. And this starts to give you a new range of architectures, ways to not only design, but to operate and control the system. And so if we look at how we can implement these, what it means is that we have the option to move away from just using things in a single traditional way to using them in a wider range of opportunities to really give us that flexibility. You still have to think about integration, because we can't just have a bunch of individual control systems out there doing their own thing. And so, where we did have more of a conceptually centralized system, there was actually no one single center, but it was centralized from a balancing authority type perspective. What we can start to look at now are layered controls, where maybe we'll allow some level of autonomy at one layer that interacts with the next layer up. And this becomes a really interesting perspective from control systems, because it gives you a lot more options for what you can do. This also potentially gives you a reduction in single points of failure. Arguably, you can have more complicated failure mechanisms, but overall, if built properly, you will get a more resilient system. And so to this end, what we start looking at is how you coordinate between networks of microgrids and centralized control to really give us this level of flexibility. Because once again, while we are moving towards a distributed or more distributed environment, we're not going to just simply abandon the traditional centralized infrastructure. The life cycle of power system equipment is multiple decades. So even if we decided today to make that shift, we wouldn't be there for 40 years plus. So we have to be looking at how are we going to integrate with those centralized systems. And individual microgrids and network of microgrids really become an option for how we might be able to do this. So one example of a control system where we started to look at this was a project that was funded through the Department of Energy through the Grid Modernization Laboratory Consortium. And this was with Duke Energy down in the Carolinas. It has a rather long title of Increasing Distribution System Resiliency Using Flexible DER and Microgrid Assets Enabled by Open FMB, with Open FMB being the Open Field Message Bus. There's a lot packed in there, but what this project was really getting at was the fact that Duke Energy has an increasing deployment of self-healing systems, various forms of FLISR, and they're doing this because of increasing outages down in the southeast. Large storms are pretty common down there, and so they deploy self-healing systems to try to improve reliability and resilience. That is a traditionally centralized system, and they use a GE DMS for that. However, there is also an increasing penetration of distributed resources, and a lot of these are non-utility owned in the form of solar PV. And what Duke Energy has found is that because of the increasing deployment of these and the fact that you now have a mixed ownership model where it no longer is completely under the control of the utility, there have been challenges with protection coordination because of all of the solar and what that means for the self-healing system, specifically the lack of visibility that the self-healing system doesn't know what's happening with solar. This project, it looked at how can you coordinate the operation of self-healing systems and PV systems so that you can maintain the self-healing systems in operation when there is a high penetration of PV. Right now, there have been documented instances where Duke Energy will have to turn off their self-healing systems at certain penetration levels of PV because they can't ensure protection coordination. What this project did is it's in the process of using the Open Field Message Bus, which is a publish and subscribe system, and it allows each of the individual reclosers into the field to broadcast, or I should say, to publish its current status, either open or closed, and the other reclosers can subscribe to the status of other reclosers in that area, meaning the reclosers that are on adjacent circuits for which reconfiguration could be a possibility. In this case, we ended up with 4 distribution circuits and about a dozen reclosers. The key with this is that if for any reason the self-healing system were to reconfigure the system, or even if there's an outage and it triggers a recloser to open, because of the Open Field Message Bus and the fact that this is all being done out in the field, within 1 to 2 seconds, protection coordination can be reestablished. And this is done because each of the reclosers knows the near real-time status of the reclosers for which it needs to coordinate with, and based on that, it can change its protection group settings. So this is a form of an adaptive protection scheme that's being implemented in a distributed manner in the field. Add to all of this, there is in fact a microgrid operating in here, and that's part of what has to be on what we call the Open Field Message Bus harness. All of these type of operations allow you to ensure that these distributed operations are not interfering with the centralized self-healing system. Now, the interesting thing about this is that there are arguably other ways this could have been solved, but the challenge with that is that they do not scale well. And what I mean by that is this is a relatively small instance of 4 distribution circuits, a microgrid, and a dozen reclosers. You could bring that all the way back to the centralized self-healing system in the GE DMS. However, if you start to do this at scale, while you can get away with a couple dozen points coming back to the DMS, if you were to scale this and bring tens of thousands of points, you run into some real scalability problems. So by offloading some of the controls out to the field, this really increases the options for how you can operate the system. This project is nearing its completion. The field demonstration was delayed, as often occurs, not because of the technology, but because of battery considerations. However, with that said, the the public utility commissions in the Carolinas have allowed for Duke Energy to obtain recovery on these type of systems, which means that Duke Energy is now in the process of putting together follow-on projects that are ratepayer funded based on this technology. So this becomes an example of where you can start to see microgrids playing with renewables and how do these things operate together. Now, expanding on that, this was an example of the system here. It shows the various configurations, but you get a sense of the complexity of this system. But where I was going with this is that the next step for this is to look at how can you not just have one microgrid, but multiple microgrids. And this is a follow-on project referred to as Citadels, and this is a project with the Electric Power Board of Chattanooga. This is building on the work of the earlier project where you were looking at how to control individual distribution assets in the form of reclosers, and now we're looking at how do you coordinate multiple microgrids in the field, and how do you coordinate their operation to support bulk system operations, but also to support standalone operations when you lose the bulk power system. Now here we start to move into an even more interesting control environment, because in the previous project we were looking at the utility system adapting as necessary to meet the needs of the non-utility systems, the solar. In this case, what we're looking at is collections of microgrids that are mixed ownership. Some may be utility owned, some may be customer owned, and some could be third party owned. And the question is, how do you start to get all of these different microgrids talking to one another and collaborating in a way to achieve goals? And so in this project, we used, once again, the open field message bus. And this open field message bus, once again, is the publish and subscribe system that allows you to publish information that any other object on there can subscribe to. The key with this is that it is the infrastructure that allows you to talk with other agents. It doesn't tell you what to say. And so it's not a control system. It's really a collection of standards-based architectures that allow you to implement the Internet of Things. However, you do it in an industrial control system. And that's what the Citadels project is looking at, is how can we implement microgrid controllers connected across an open FMB harness, all using commercial off-the-shelf equipment such as Schweitzer RTACs, their SEL 3354s. The next question, though, is if you do that, what do you have them say to one another? And for this project, what we wanted to look at was, instead of looking at some type of centralized control algorithm that you would decompose through traditional control theory, instead we wanted to use consensus algorithms. And the reason is that because of the fact that you have a mixed ownership environment, there's not going to be a single control algorithm. And what I mean by that is the way, or the process of controls that are implemented by the utility may not be the same as the customer. And additionally, the utility may deploy multiple controllers that are different vendors. And so you need something that is not locked into a single control structure. And so with the collaborative autonomy or consensus algorithm concepts, the idea is that information is shared between agents, in this case, microgrid controllers, and based on the information they share, as well as their local control objectives, resources, and other factors, they all exchange information as well as intermediate decisions, all to come to a consensus to say, this should be the next set of operations that we want to do in order to move forward. And that becomes actually a really interesting idea, because now you're actually having non-utility assets that can contribute at some level to operational decisions. And so this is where consensus algorithms become very valuable, because they allow for other factors such as proof of authority, proof of trust, so that you can properly weight operational decisions, because utilities, they will still, of course, have the final operational control over assets, at least in current models. And so they need to be able to say, if we have a collection of microgrids participating, they have to be able to weight the value of those decisions. So for instance, if you have a non-utility microgrid that has a history of having poor measurements, maybe for certain classes of decisions, you would reduce its weighting factor in the decision process. Now, it's a little bit more complicated than a simple weighting factor, because there's a lot of algorithms that go into consensus. There's a whole range of algorithms out there. In fact, there's a lot of these are used for cryptocurrencies and things of that nature. So we're really tapping into a deep existing domain knowledge, and we're trying to figure out how to best apply it to this example. The example that we've had for this is what we're calling a self-assembly of microgrids. In this scenario, what you have is a loss of the bulk power system and a number of microgrids that have their own independent islands formed, stable frequency and voltage. The assumption is that this is mixed ownership, so you have some of these are utility owned, some are not utility owned. And each of these is going to have its own operational goals, its own willingness to participate. And the question is, would it be possible to assemble these microgrids so that you could increase the runtime of critical end-use loads and overall make for a more resilient system for the critical loads that are supplied? Now, as you can see, there's a lot of different potential answers for that. You could very well see in a mixed ownership model where you could have one microgrid that says, I have enough resources, I'm going to run on my own, I don't want to interconnect with anyone. You could have another microgrid that says, I don't have very many resources, I do want to interconnect. And then you could have microgrids in between that say, I've got some resources, but I could potentially benefit. And this is where the benefit of the consensus algorithms come in, because you can deal with considerations such as greedy actors, people that aren't necessarily interested in the overall global goals. And so this allows us to have an environment where in step one, all the microgrids are exchanging data between controllers. No one's agreed to take any controls yet. They're just agreeing to participate and exchange information. So the next step is each microgrid goes through and it says, what microgrid, if I could only connect to one other microgrid initially, what microgrid would I want to first interconnect with? And this is where this approach makes a lot of sense, because you could see each microgrid could calculate this differently. One microgrid could do a full economic commitment unit dispatch, something very, very complicated, whereas another microgrid might just say, I always want to interconnect with microgrid number 4 because of past experience. And so you end up with people having many different possible ways that they could select this. And so you get to step 3 that says local result. Each microgrid through its own process says, in order to increase the runtime of my critical loads and any other objectives I have, this is the microgrid I would want to first interconnect with. Then you get to step 4, which is the consensus. This is where all of this information is exchanged between the microgrids, all of the results, and they go through and look at everyone's selection of who they think they should interconnect with and globally come up with what is the best set of microgrids to first interconnect. And so this becomes an interesting process, because what you're saying now is that everyone has agreed that they'll share information, and now they have to agree on their consensus list and how much they're willing to participate. And so, for instance, you could have a microgrid that says, I have 10 megawatts of generation, but I'm only willing to share 4 if I were to interconnect with someone else. And so you have all of this level of participation that would go into this consensus. And through this, all of the microgrids come up with an agreement that says, yes, given the current conditions, this is the first set of microgrids that should interconnect. And then the system iterates through that. And by doing this continually, microgrids will form up until you're at your, call it, optimal solution. But this is a time varying process. So over time, what you could see is that some microgrids might disconnect, new microgrids might connect. And reasons for this are, if this is an outage that goes into the nighttime, a microgrid that at the solar peak that has a lot of solar, it may be a resource for other microgrids to interconnect with. But at nighttime, it suddenly has a large load that's a low priority and no generation resources, so maybe it would be disconnected. This is all done through the consensus. And this becomes a very dynamic and complex control environment. To give a sense of taking up one level higher, this is what the architecture of this looks like. This is where you start to look at things from a conceptual level of, as you're going through this consensus, this decision making, taking these actions, how does data, well, let me start from the top, how does energy flow between various blocks in here? So you've got distribution substations, microgrids, utility owned, non-utility microgrids, reclosers, DERs, loads. How does data flow? How does it actually exchange between devices? This is where we can see For instance, this line indicates that there is a peer-to-peer at the application layer communication between microgrid controllers that are utility and non-utility. And then you also have control lines. And for instance, here you can see that if you look at this control line for the reclosers that interconnect microgrids, what we're saying is that that control signal can only come from the microgrids that are owned by the utility or the distribution operations center. This means that you cannot have a non-utility owned microgrid initiating switching across a utility system. This is important because this becomes a large factor in how you're examining the consensus algorithms. Who has authority to do what? How do you implement it after a consensus is made? And so this begins to give you some of the control considerations that you need to look at, and this is really going to impact your resiliency and your ability to integrate the renewables. And the reason for that is it goes back to this heterogeneous operating environment. Not only do we have mixed ownership and mixed operational goals, but you're going to have microgrids with different electrical characteristics. This goes back to that example I said before, is that you could have a microgrid that has a large penetration of solar. So you could have one microgrid that's all rotating machines and electrically relatively stiff. However, you could have another microgrid if it has a large penetration of grid following inverters and only a few grid forming inverters. That can be an electrically weak system, which means you have to consider the dynamic stability, both steady state and transient, of that system. These system dynamics become very, very important. And this has become a real challenge in inverter-based systems, is that grid following inverters use phase lock loops, and they have to have a strong central primary frequency to lock in with. As you get to electrically weak systems, you start to lose that and they become unstable. And the challenge of grid following inverters on weak electrical systems has been known for decades now. It's a real challenge. But you do also have grid forming inverters. They are able to form their own stable voltage and frequency, and through fast injection, they're able to operate in an effectively low inertia system. But there's still a trade-off between the high speed of that operation with rotating machines. So the consensus needs to take into account these type of constraints as well. And what you end up with is a very complex control environment. And so while you can definitely use microgrids through these advanced controls at the edge to implement some very new resiliency operations that will keep operations going when there's an outage on the bulk system, it also allows you to integrate much higher levels of renewables because you've got intelligence at the edge that can coordinate with the central system. Now, one of the big challenges, and this is setting up for the next part of the talk, is that as the complexity of these systems arise, we're starting to have an increased reliance on communications infrastructures. There was a lot of early work on CERTS type microgrids where everything could be done with generator droop curves and there was no need for communication systems. And you can run stable microgrids like that. But as we look to optimize the system, create a more flexible system and do more and more with it, we're going to have more of a reliance on the communication systems. And so the question naturally arises, what happens to those wonderful communication systems, or I should say the control systems that give us all this flexibility, when there starts to be a degraded performance in the communication system? And that's the next part of the presentation. I'll hand over to Gautam for this, where he starts to look at the data-driven approach to delay tolerance in these microgrid controls. So with that, Gautam, can you take over from there?
Let me share my screen. Are you able to see my screen?
Yes, it's up.
All right. Thanks, Kevin, for the introduction. So the first part of the presentation kind of highlighted what the theme of the resilience and decarbonization work seemed to have in common, which was that it looked at controls and that were enacted over communication links. Some of these applications have been classified based on their dependence on high performance communication networks, and some of these applications do fail when the communication network degrades. So the question that we wanted to answer was, would we be able to kind of enable a tolerance to delays in these critical microgrid applications using a data-driven technique? A little bit of introduction on what we looked at is, as mentioned in the first part, communication-assisted controls improve the resiliency and reliability of the microgrid. We also allows for advanced controls that promote decarbonization efforts and allowing for greater penetrations of renewables and increasing the controllability. In some sensitive applications where communication links actually close the control loop, where measurement flows from the sensors to a controller through a communication link, and again from the controller, the actuation signal goes to the devices through a communication link. It is imperative that the communication link has low latency to ensure successful operation. But not all applications are insensitive to delays. So some operations do maloperate because of delays, and if they are resilience-driven approaches, you can see a reduction in system resilience. So why do we need microgrid controls to be delay tolerant? As Kevin previously mentioned, that the transition to advanced technologies, it's not going to be fast. So we would have microgrid controls that need to be implemented on legacy communication networks where their delays are high and bandwidth is low. And in some places, implementing these microgrid controls can over a low latency network can be prohibitively expensive. So we chose one specific application that was very sensitive to the delays, which will be explained in the next slide, to look at how we can start to first parse the system into its several subcomponents and use co-simulation to study them, and then to analyze what would be the best method to impart tolerance to delays. So we use co-simulation to study the interaction. A little bit of definitions. Co-simulation is a method to couple different simulators of systems or federates, which each of them simulating a single subsystem. With the co-simulation platform being Helix that can allow for time synchronization and data exchange between the different models that can simultaneously simulates its portion of the interdependent complex system. So co-simulation allows for models that have different domains, temporal attributes, running on different machines, computers, operating systems to basically simulate together, and allows us to look at how these interactions are expressed and how each other's behavior influences one system or the other. For this work, we used GridLabD for the power system or the distribution system simulation, NS3 for communication system models, and Python for the controllers and the data-driven algorithm. So a little more on the co-simulation portion of it is why are we using co-simulation to study the interaction, is that we would want to know where the problem happens, where the delays happen, and what is its influence on the successful operation of the microgrid. So there are different domains in which you can see problems and that can be captured by using co-simulation. On the networking side, you can see idling, pending, and queuing issues during data transfer, retransmission, and collision that can cause delays and data drops to happen. On power, we can look at consequences of these delays in terms of voltage, frequency collapse, or cascading outages. We can look at control issues where break-in sampling or sample rejection can happen, where in the iterative control loop, you can see that some of the measurements don't reach on time, and that can cause convergence issues, or some of the samples that come in do not reach on time, so a previous sample is taken as a substitute, and that can increase the computation time. On the delays, so there are multiple causes of delays that can happen in the system on the communication side on the propagation or the process, and also we have to deal with data drops where the data is lost. And you can also look at how it impacts both measurement and actuation. So we've used a fairly well-modeled communication network. And why do we need to use communication models in co-simulation is because we cannot directly substitute certain fixed delays as like a transfer function type substitution to understand the relationship of microgrid operation with respect to communication delays. Some applications do have uncertain delay outcomes. They are time varying, and the sources of delay is not known. To further talk about delays, there are multiple ways delays can occur in especially in smart grid communication. The process delays are caused by your on the Hello?
You're cutting out a little bit, Gautam. You might turn off your video, see if that helps.
All right. Can you hear me properly? I don't have anything on. I mean, it's just PowerPoint, just the PowerPoint is on.
Well, we can hear you now. Go ahead and try to keep going.
All right. So I stopped at proper process delays. So process delays can happen in the communication link due to increased data traffic. Basically, a lot of collisions happen. The data is delayed because of pipeline issues, or if you have multi medium communication networks which have different communication technologies, you can have a lot of translation translation issues that can cause computation-based process delays. On the propagation side, which is directly relates to the resilience to extreme weather events, is the loss of physical communication nodes that can be part of any extreme weather event or interference due to electromagnetic interference due to thunderstorms or solar flares, and the distance between the nodes and the obstacle also plays into this reason. On the cyber attack side, there are availability attacks that can basically increase the latency of the system, can create a dissonance between data being transferred into the control loop process. Let me talk about the application that we have chosen to study this problem. So this is the networked microgrid system where you have these microgrids that have combinations of batteries and solar PVs. And the algorithm is such that a centralized controller, which basically receives measurement from GridLabD, now is able to calculate what the generation mismatch is, and then tries to, in the event of a PV loss of PV, tries to dispatch the battery to offset that change in real power, and thereby upregulating the frequency. As a second line of defense, there are also grid-friendly appliances that can respond to either a control signal or internal under frequency load shedding set points that can trip to mitigate the variability in solar. So a successful operation looks like this, where this portion is where the microgrid is formed and operating, and at 4 seconds the PV drops. And as you can see, the orange, the PV drops right over here because we are operating in a very low latency network. The microgrid controller is now able to receive all its measurements from the generating units, the DGs and the PV and the other battery, to kind of compute what is the drop in generation and kind of offset that by dispatching the battery to that right point. So because this happens, you can see that the system frequency is pushed back into nominal operating range fairly quickly. However, this is not the case when the system actually doesn't have has high latency. In this case, you can see that the dispatch of the batteries don't happen within time, and this is mainly due to the 1547 under frequency limits that the grid following inverters respond to, where over 160 milliseconds at 57 hertz, I think, yeah, 57 hertz would cause the inverters to all the inverters to drop, and therefore there is a rapid collapse in frequency because all the generation sources is lost. The backup control here, this is how the system would look if none of the GFAs was operated. But however, the GFAs can operate and restore system frequency. However, that comes at a cost of loss of end-use loads and therefore resilience. So what is the way to, what can be done to increase the tolerance to delays in such critical applications? So we mainly found that there are 3 methods that are typically available for systems that are sensitive to delays. So on the networking side, you can use software-defined networking or dynamic routing or advanced distribution coordination, which are basically operate on the data layer of the network architecture to allow for the data packets to take a lower latency route into the controller. On the other side, next step would be to use a change in control architecture where backup controllers can compensate for periods of communication degradation by switching to local autonomous or a distributed type control architecture using reduced network inputs. And the other the traditional control theory type option would be to use a robust controller where the problem of delay is folded as or is considered to be an uncertainty, and that is wrapped into the plant model itself for which the controller is designed, or the adaptive control where the controller parameters change in response to how the output varies. Porting these to these sensitive applications can be difficult, mostly because many of our systems that look at controls like these do not have accurate models, plant models, and they are computationally intensive. And some of the networking techniques require the communication network to have high redundancy and high data latency requirements, or more stringent data latency requirements to begin with. We also wanted to look at if this method can determine the degradation of the communication networks without ever quantifying what the communication network attribute is. That way you can keep your system operating successfully even without ever looking at being delay agnostic. So the method that we decided on is the use of measurements to prevent maloperation to delays. There are several methods that can be there that can kind of predict how the system should behave during a successful operation, and some of these are computationally feasible. So the basic idea is to have a prediction and controller that is local to the device, in this case a battery, that can predict the evolution of parameters based on past successful operation, and to predict or also to determine if the predicted response and the current response match, and to talk and to decide whether to operate using a more centralized communication-based microgrid controller or a local terminal measurement-based local controller. The data-driven technique that we have chosen is the dynamic mode decomposition, which correlates to the Koopman operator. It provides a linear and finite dimensional representation of the linear system based on a rich set of measurements. The time series data, in this case, we are looking to predict frequency. So we are looking providing the DMD with the time series data of frequency that can basically describe the nonlinear system as a forced linear equivalent, where the behavior is modeled as the superposition of leading dynamic modes that are governed by dominant eigenvalues. So the one advantage of the system is that this method is that it is computationally not intensive, and also no prior knowledge of the system is required. So you can get edge measurements and basically predict the evolution of dynamic parameters with fair accuracy without having to know what the plant model would look like. Let me talk a little bit about the prediction of frequency. So the frequency prediction takes up a few steps. So the first step would be to feed it with frequency measurement from a previously known control operation. So you have a set of measurements that kind of tells the controller this is how the system frequency at the terminal of the device behaved for a successful operation. One advantage of this is that the actuation in the system is also built into the frequency measurement itself. So that basically allows for the system to for the DMD to predict what would be the system behavior if a successful control has happened. The first step in doing this is to do the Hankelization, which is to convert the univariate frequency time series data into multi-dimensional augmented data matrix that is shown here. Basically convert your univariate data into slices of size L into column vectors that are lagged by one measurement, and also to create another one that is X prime that would be basically time lagged by one time step. So this basically allows you to define a mapping matrix K, which basically advances X to X prime, or X of T to X of T plus 1. And there is a way to find the value of K, which basically represents the dynamic mode, which basically represents the best fit linear operator that corresponds to coherent dynamics structures, which are decomposed dominant repeatable low dimensional behavior of the system that is obtained from a very much more higher dimensional nonlinear system. So using this K, using the K, so the objective is to find out what the K vector is, and that is done using the singular value decomposition, where you can convert your initial input matrix X into U sigma and V transpose, where V transpose is a unitary term. Sigma can be easily invertible, and the U can also be invertible using the complex conjugate transpose to find the pseudo inverse of X. And by directly substituting that value here, you would be able to find a reduced order approximation of this the K operator or the mapping matrix to find an approximate linear operator that can predict the behavior of the system. So using that, you would be able to iteratively multiply an initial data set to predict what it would look like one time step into the future. And you can do that multiple times to kind of see how the system is evolving into the future. So once you have this data set that can, the predicted frequency data set, now you can basically determine if your system has operated in a successful manner or not, based on how the trajectory of the predicted and the measured frequencies change. So let me talk a little bit about what the framework actually is. So the first portion of the framework is the GridLab simulation model that basically interacts with both the dynamic mode decomposition, the data-driven module, and the controller module. The controller module basically consists of two controllers, a local controller that sits on the terminal of the device, constantly monitoring frequency at the terminal itself, and also making the determination if the control signal coming from the centralized microgrid controller is dependable or not, based on how the system reacts to delays. And a centralized controller that basically provides the battery set points based on real power measurements that are passed on through via the communication module. The data model is, as explained, basically captures a successful operation of the a previously known successful operation, uses that frequency evolution to predict what frequency it look like at an event start, and to determine if that frequency matches with the measured frequency, and to make a selection whether a local or a centralized controller input needs to be chosen. Second. So here are the two figures shown here. The first figure shows the field implementation of the proposed framework. So basically, the idea is that the communication provides all the inputs to the centralized controller, which provides the actuation signal, and that goes on to the controller. The local controller also looks directly at the terminal frequencies and is tied to the inverter with no communications attached. So the assumption is that it is basically a computer that's, or like an algorithm that sits in the computational engine within the battery itself. And the co-simulation setup is the centralized controller talks to the power system model using the NS3 communication model, while the terminal controllers talk to the GridLab models directly without any delays, because they are at the device level themselves. Using that, we were able to predict, to get a reduced order approximation of the input or the measured frequency to predict evolution of the frequency based on previous historical input. The DMD is successfully is updated for each successful iteration. So based on this, we were able to predict how the system would deviate with and without the delay tolerant controls in place, where the system would change its status between 0 and 1, 0 being respond to the centralized microgrid controller, and 1 being respond to the local terminal controller, because you cannot there is delays in the system that's causing the system to react unfavorably. And you can see that there's a conservative and dispatch to the batteries that are dispatched based set points that are dispatched when the local controller selects the prediction is does not match the measured frequency values, and that's the same for both these cases, and the successful operation can be ensured by that. The advantage of this is that if your system has grid-following, grid-friendly appliances, you would be able, you would see a loss of those GFAs in response to the under frequency. In this case, you can see that at this point, at 57.5, a little over a few milliseconds, the GFAs trip out basically for a 320 kilowatt of PV, 300 kilowatts of grid-friendly appliances are dropped. Therefore bringing the frequency back to a nominal value. This is shown right here. You can see that the blue line shows that there is a drop of around 300 kilowatt in the networked microgrid model in response to the low frequency event. If GFAs are disabled, you would basically lose the entirety of the load because your grid following inverters would have tripped. However, using the grid, the delay tolerant control, you would be able to bring the system to successful operation based on local controller measurements and avoid that loss in resilience. A little summary is that we proposed this delay tolerant controls framework that can enable advanced controls that are delay sensitive over legacy communication networks. It allows for reduced communication infrastructure requirements and basically ensures successful operations in terms of delays. The dynamic mode decomposition is not only computationally inexpensive, but is also allows for a greater offers a greater insight into anomalous events in the system environment because the actuation of controls is also folded into the measurements, and you can kind of basically see how your frequency behaves in response to that actuation. There are other prediction techniques that are available, auto-regressive methods. That would be the next step into seeing if there are other prediction techniques that are less intensive and also faster. I can also predict far into the future with sufficient accuracy, and to look at other latency sensitive applications. So mostly these latency sensitive applications have been generation load controls that basically mitigate voltage and frequency collapse fairly quickly. Yeah, I'd like to thank the AGI for setting this up. I am part of the PNNL WSU DGRP program. It has been a wonderful experience for me, has helped me collaborate with a lot of scientists and engineers at PNNL. The brown bags at PNNL have been great. I basically was stuck in a problem. It was resolved because I reached out for help after seeing one of the brown bags. Thanks to my advisors and the team at PNNL that helped with this work. Yeah, we can take questions now.
I know we're a little short on, we only have about a minute left.
Yeah, we can stay a little longer if you guys can. If not, we can get you the questions.
I'm afraid I actually have to go I have a hard stop at 12, but I can take any, if people have my email contact, I'll take any questions offline. Yeah,
Kevin, if you want to drop that in the chat. Well, there are a couple questions that I don't, a couple for Gotham. Let me see. Kevin, you answered a couple of yours in here already, I think. So I think there's a question about assigning the slack or reference buses in each microgrid. And I don't know, Kevin, if you answered that one.
Yes, I talked that one. What I said is that when you're doing a dynamic simulation, the slack bus only really exists for the initial power flow calculation. After that, it really is about the dynamics and the differential algebraic equations. So in an implementation, you typically make the slack bus connected to a large generator, and that generator has to be able to supply whatever the slack bus solution is. If it doesn't, that's when you start to get into numeric stability issues of your simulation. Basically what it's saying is you just haven't built a very good model, and it can collapse if you don't do that properly. One other thing I'd say is that if you make a mistake and put a swing bus somewhere else and it turns into a true swing bus, you're not going to have very many dynamics on the system because it's able to source and sink infinite amounts of power, and you get very flat dynamic simulations.
Okay.
And I apologize with that, I have to drop off, but I did put my email in the chat, and I'd be willing to follow up with any questions that people have.
Thanks, Kevin. Thanks for your time and the great presentation. Let's see, there's a question about Gotham on slide 21. How does the controller architecture and design differ in decreasing the tolerance band, since one is an integral part of the other? Or one is an integral part of?
Oh, I assume that he means to say with the different like a distributed controls can also have a centralized controller. Is that what he means by it?
Sanjeev, I don't know if you want to add more to it.
Yeah, thank you, Prasanna. So Gautam, so it's basically about like the architecture, the controller architecture and the controller design. You said that you can increase the tolerance band. So
right.
I don't know what are the differences between those.
Yes, sorry. Thanks. Thanks, Sanjeev. The controller architecture basically describes how the measurement, actuation, and the controllers are laid out. I'm sure you know that there are centralized controls that where all the measurement is collected, the controls or optimization is performed at a central node, and then actuation are pushed out. So that is what I meant by the architecture itself. However, the controller design is more about the traditional control system controller theory, where you are basically trying to design a controller K in response to where you can for feedback control of a y of t to an input x of t. So in those places, the controller design would allow for delay tolerance by either robust control, where the delays are folded into the plant model as uncertainties, or adaptive control, where the controller parameters usually change, the time constants and the gain change in response to the trajectory of the output. Yeah, does that answer your question? Thanks.
Yeah, there's a question about COSIM. Does COSIM utilize OpenFMB?
Oh, no, it doesn't. I'm using traditional prototypical communication systems. So as my first part of my work at PNL, I looked at common implementations of smart grid communication networks in North America, mostly to see at look at, okay, how is an AMI type communication network set up? How is a distribution SCADA system set up? How is a distribution automation type smart grid communication architecture set up? So I've been using a few of those NS3 models to co-simulate my communication networks.
Okay, what are key characteristics of dynamic mode decomposition? Is there are there limitations?
Yes. The main key characteristic would be is that you can get a fairly accurate dynamic behavior of the system just using your measurements. This basically provides a way for you to describe your higher dimensional system in terms of lower dimensional repeating dominant modes or dominant leading eigenvectors and values of your mapping matrix to to find this approximate linear operator that will predict system behavior. So, and that because it is truncated, you can also have easy computation. Because the application itself is time sensitive, you would also want your prediction to be fairly quick enough. Yes, there are limitations. The limitations here being that the limitations is in the DMD itself that I've been using. However, to use there are extensions to DMDs that can basically answer most of the limitations that DMD itself has. The one being that depending on the slice of or the window length that you choose for creating your converting your univariate time series data into multi-dimensional augmented data matrices, you would basically limit your prediction windows. And if there are significant state changes that happen during between these time slices that is not accurately represented in for that can be the correlation cannot be easily identified between say as the change of state from one state to state 2 versus state 2 to state 3. So that differences are there.
Okay, I think there are several other questions there, but I think for now we're going to stop just because I know some other people have commitments. And thank you so much for an excellent presentation and a great example of the partnership. I believe this is the last webinar of the ESIC spring semester, with exams being next week. So we wish all our students good luck finishing up all their different activities this semester. And thank you very much for your talk and for participating. If you have further questions, please feel free to reach out to either of our speakers. And thanks, everybody. Have a great day.
Thanks a lot. I'm just going to stay here and respond to these messages, these questions.
Okay. Well, we'll stop the recording, and if you want to answer the questions, you can do that.